Good afternoon, good morning, maybe good evening, based on where you are. Thanks for joining this month's ABCD AI and bioimaging community discussion. For those of you I haven't met, I'm Ken Shopman, ABRF's Executive Director. We'll have a few housekeeping and announcement slides, and then I will turn it over to Erica, Emery, and Tim to present on image segmentation. So feel free to introduce yourself in the chat where you're connecting from, your institution, and also use chat for any questions. You might have heard that we are recording today's session, and we will share that recording with everyone, as well as post it to the ABRF events webpage. If you have suggestions for future programs in this series or otherwise, please send those along to us at abrf@abrf.org. Some updates. Everyone, I hope, is aware of ABRF's revised strategy, which is built on these 4 goals or pillars. There are task forces that are actively involved in creating the activities and objectives that to support all of these. You'll hear more from them next month at a town hall where they'll be giving a progress report on some of the things they're working on. And you'll also start to see some changes, for example, to the ABRF website. One of our task forces is looking at making some improvements there as well. This is just another view of the goals and objectives related to the 3-year plan for the ABRF strategy. Some upcoming events later this afternoon, if you'd like to have more ABRF, we have a membership orientation program, whether you're a new member or looking to find out different ways to get involved in ABRF or what ABRF has to offer. Please join us for that program. And then you can see the rest of the events that are coming up for the rest of this month. Some terrific balance of education programming, peer networking conversations, mentoring conversations, a preview of the upcoming annual meeting. Committee members will be discussing the particular sessions that they're looking forward to. And then continuing our ongoing series on DEIB education on bystander intervention. So all of those details, registration, links, and so forth are available at the link you can see on the screen. It's not too early to be thinking about the ABRF chapter meetings that'll be taking place during the rest of the year. Kicking off with CSER, the Southeast Regional Chapter, will be back in Atlanta in June. And then you can see the rest of the calendar. Some of the dates aren't finalized yet, but continue to monitor the chapter web pages. And of course, we'll be sharing that information with you as those details are finalized. But lots of options to connect locally. If you haven't been to a chapter meeting before, they're terrifically valuable opportunities to meet your colleagues and also corporate partners that are really looking to hear from you about what's working and what you're looking for in a new technology to make the most of the investments you've made in equipment in your facilities. I hope you're participating in the online core community. There are many groups in imaging issues and topics, as well as dozens and dozens of other groups where you can post questions, get immediate response from the 3,500 plus ABRF members throughout the country and around the world. If you're facing an issue, chances are someone else in the ABRF community has faced that as well, and they're always willing and open to share ideas and suggestions. So please explore the community. Contact us if you have any questions or issues connecting. Some brand new information that will be publicized has been posted in social media, and you'll be seeing it in today's ABRF newsletter. The executive board made a couple of decisions to help boost participation and engagement in the upcoming annual meeting. First and foremost, we will hold or freeze registration rates at their current early levels, so they would not increase. They were due to go up after January 16, but they'll hold because we want to make it as feasible and as realistic for folks to participate. So you'll be able to save a little bit there. In addition, the Education Committee and the Meeting Committee have extended the poster abstract submission opportunity through the end of the month or through the 28th. So if by presenting a poster, you're able to get approval to participate in the meeting, please do that. Please share. I think the committee is very receptive. We have abundant space for poster presentations during the meeting. So if you have an idea, if whether it's research or a novel method, technique, or protocol that you're using in your shared facility, please put that together in the form of a poster abstract. The education committee would be happy to look at that and invite you to participate. So again, two very recent decisions that we wanted to share with everyone during today's program. All right. We also have, of course, several pre-meeting workshops. If your schedule permits to join us Saturday, the meeting schedule shifts a little bit this year. We begin with the pre-meeting workshops on Saturday, March 28th. There are 3 options, as you can see on the screen. The Lean Management Program is back for a 5th or 6th presentation, always a very popular program, together with the other topics you can see as well. So space will be limited for these because they're designed to be group work and interactive. So hit the QR code, go to the website to learn more about those if your schedule permits. Oh, mercifully, that's the end of that. So now I'll turn it over to Erica to introduce today's presenters. Thank you, Erica.
Thank you, Kim, for the introduction and update. Tim, could you share your slides? Okay. So I would like to take this opportunity to briefly highlight the upcoming ABRF 2026 annual meeting taking place in this March. So there will be 2 Like My Crosby research group sessions focused on image analysis workflows for my Crosby data and statistical considerations for my Crosby data interpretation. So we will discuss how to support researchers or core facility in develop rigorous, accessible, reliable, and high throughput image processing pipelines across diverse research areas, and we also will provide practical guidance to strengthen statistical rigor across the MyCrosby data workflow. And also, due to the strong interest and popular demands at ABR 2025, this year we're also offering the AI and bioimage analysis mini workshop this year. Space are limited, so register early, sign up early. And Tim, next slide, please. Okay, so I'm very excited today about today's ABCD seminar, and thank you all for joining us today. So the topic is segmentation with thresholding in ImageJ, and it is my pleasure to introduce our co-presenters, Emery In, Director of the Facility for Advanced Imaging and Microscopy at Virginia Tech, and Tim Chaya. He is a Super Resolution and Confocal Research Associate at the University of Delaware. And before we begin, a brief disclaimer. ABRF and LMRG are not the sponsor and endorser of ImageJ or any software mentioned during the ABCD seminar series. Again, please feel free to post your questions in the chat, and we'll address questions during the concept chat breaks throughout the presentation. And with that, Emery and Tim, please take it away. Thank you.
Thank you, Erica. So yeah, Tim, University of Delaware, and so we're gonna move into this. There we come on. Maybe, there we go. And so we're gonna do a little background on ImageJ just before we dive into all the thresholding and image segmentation. And so before we even open ImageJ, one of the things we need to consider is the data you're acquiring that you want to analyze. And so before you even think about your analysis, thinking about the standardization and handling of your sample prep, optimal image sampling, so the best pixel size for the objective and what data you're trying to acquire. You have good contrast. Can you see the object you want to analyze over the background? And you have good controls. And I think this is one to drive home for a lot of new microscopists and as well, is you want to say there's a difference, but if your negative control looks like your positive control, then it's not a good control. And so now you're ready to start analyzing, and this says before you even image more, and I do recommend this from experience as well, of potentially, if it's a new protocol or procedure, to do a pilot. Run through, have your 2 controls, run your analysis, and use that to help hone your things before you spend hours or days or weeks putting together a data set that you can't analyze. And so ImageJ, or Fiji, was developed by Wayne Raspin at the NIH, as well as others. It's a recursive acronym, so Fiji is just ImageJ. What's nice about Fiji is it has all these extra plugins that you don't need to download separately. And so you can add more plugins easily, but there's so much built into Fiji that for the majority of users, just having Fiji on its own is the way to go. Oh, there we go. What's also great is the community that surrounds ImageJ and Fiji is wonderful, right? We have a global network of people who are using the software to help analyze images and answer similar questions. And so obviously there's the user guide and tutorials from ImageJ, but also the ImageJ forum itself. And so it's an online forum where you're going to be able to ask a question or at least look to see if someone else has run into the same question before. What's nice about that is there's different tags to help kind of sort this all out. And so if you just care about Fiji on its own, you can go in and just look at the Fiji related ones or get more granular with your question. And they're post daily, hourly, whatever. And so if you get stuck, there's people out there who have been through the same problem, similar to our other LMRG members, right? They're people who experience the same issues. And so we can rely on a communal expertise to help get there. And so where does ImageJ fit into this analysis, bioimaging, processing, and pipeline? So you've got your original image. So these are just some chloroplasts. You can do some pre-processing, thresholding, a binary process to help split your objects up, and analyze particles. So now go through, say what chloroplasts are there, get a count, say that there's 9, and then apply that those thresholded regions of interest to your original data and get some quantitative information. And so all of that can be accomplished in ImageJ. You can go straight from the microscope, dump it in ImageJ, and get to work. And from that, you can extract area, intensity, all these other metrics that are going to give you the power to do quantitative microscopy on your data. For those not familiar, ImageJ, when you load it, it doesn't look like it's a real high thrills piece of software. It's very basic looking. And so you've got just this regular toolbar, but within that, you can have all these submenus, which then lead to more menus. And you can open your images just straight in ImageJ by either going to open and using bioformats, or just dragging and dropping them into the toolbar. From the edit menu, this gives you all of your copy, cut, regular edit commands, as well as defining background and foreground colors and the color of your outline. So my default outline color is yellow, but if that doesn't work for you, you can make that something else. In your image options, this allows you to manipulate your selected image, whether you just want to crop down. So if we think about our chloroplast image, if we just want to go to one of those chloroplasts, we could crop that out. We could duplicate it. We could Z project or make a subset all from this space. And the one tool that we're going to use quite a bit, or that we're going to discuss quite a bit the next hour or so, is the use of thresholding to help improve your analysis, right? And so that can be done by going to adjust threshold or shift T. One of the other tools as we move across our submenus on the top is pre-processing. It's not uncommon that your raw data just is going to need a little help before you can make those thresholded images to start to analyze. And so you can find those in the pre-process. And that's going to give you medians, Gaussians, FFTs, other types of filters to help clean up the raw to process into a binary. From there, once you have that, you can then go into the analysis space. And so set measurements gives you about, I think it's 17 different measurement options, and you can check them all. You can check a couple of them. So if when you get your output, you're not weeding through tons of different Excel columns. And so once those measurements are set, you can then go to analyze particles. And so it's going to use that image you generate and extract information. If doing it all but manually, we've gotten to the point where we have all these plugins. And so they're, from a quick Google search, near 1,000 different plugins, potentially more. And so there are a bunch built into Fiji, and you can add more as needed. And so you can just pull on that drop-down menu and go in and use those plugins, and they give you a generally a guided user interface that you can go through and process your data. The tool that I probably use the most in my analysis is the search bar. And so instead of trying to navigate the menus just to hit L and type median or Z project, whatever, you get used to navigating the space pretty quickly from a keyboard if trying to remember all the menu drop downs is a bit much. To do your object detection with thresholding, we're going to take your grayscale image and just turn it into black and white, or a binarized image where a 0 is your background and 255 is your foreground or your object. And so there are different threshold models that use the intensity histogram to help determine what is an object and what is not. And so they're available through the thresholding command or Shift-T, and that'll open up the tool that'll allow you to do this thresholding. And then once the thresholding is done, you can do some additional binary processing, right? So we're in the middle here where it says thresholded, and you can see that in the upper right, the top half of this image, we have these chloroplasts merged together. You can run a watershed, you can fill holes and help divide those objects up before you start extracting information and making your objects look bigger than they're supposed to. When and how should you use thresholding? And I think that's a good place to start. Is it's a good tool when you want to be consistent, right? We could manually go through and threshold each image by adjusting a slider, but then it's going to be biased and it's not going to have the consistency that we want as quantitative microscopists. And so this allows you to go through and say, I'm using this method, apply it to all of the images and extract that information. It's very common in large scale counting and other measuring tools that you're doing any sort of segmentation. You need to choose a model that's going to work best for your objects and samples to give you the best reproducibility and rigor. And so we'll get into kind of how you discern what that best tool is. And so on the right here, we have an image and we can see that there's maybe a dozen objects in there. Well, they're kind of fuzzy, but we want to segment them out to do some sort of analysis. And so if we drew a line in image J and did plot profile, we could get this these peaks of where the centers of those objects are. And then we would define a threshold. That's what this dashed red line is. So we're saying that anything above that dashed red line is an object and anything below is background. And so that's kind of a visual way of what we're going to be doing in the next couple of slides here. The threshold menu itself, or command, opens up when we see this histogram that shows our intensity values. So the example image here is a 16-bit image, and so we can see the 65,000 plus values, and you can see what's selected by what's in that red box. There's a drop-down menu that shows all the available threshold models, and you can, when you have the image open, it'll select the color as to whether it's black and white, or in this case, it's going to show red. So red is going to be defined as an object, and black is not. For most of us, because we're looking at fluorescent proteins or other fluorophores of some sort, we're going to have a dark background and our signal is going to be light. So I typically always leave dark background checked. And then the next one is when you open your image in image J, sometimes you're going to adjust your brightness and contrast. You can tell the threshold tool to not reset the range and use that adjusted image for your thresholding output. More often than not, though, I'm going to threshold off of the raw, so I will leave that unchecked. When using 16-bit, and this is important, is to check this so that it uses the histogram appropriately. We want to make sure that we're selecting the appropriate bins that show our objects. For those of us who are doing volumetric imaging or time series, we want to also consider, are we going to generate a threshold for one image or the whole stack? And so if you check stack histogram, it's going to look at the entire volume or time series and generate a single histogram, and then you'll make a threshold off of that. Typically, and with this checked, you'll get this other option shown up. Typically, I'll calculate threshold for each image unless there are certain other things I'm trying to track. You can convert just the current open image, the single slice, same as before where you have your black background. It can output a list of thresholds, but the one that I think is the most useful is to create a new stack. So that way you have the original image to go back to if you're trying to do some sort of analysis. You can also calibrate your pixel values and generate data based off of that, or you can use just the raw values. So if you don't make any adjustments, this box isn't going to change too much for you. From this dropdown, there are, I believe it's 14 different segmentation methods. Some are similar. So default and ISO data work on a similar mathematical principle. And others are good for, depending on how your histogram looks. So if you've got a bimodal histogram, you're going to lean towards Atsu. If you're going to have a single mode, you're going to lead towards triangle. And so these are things that you'll have to go through and essentially play around with your data to see what is going to give you the result, not that you want, but is going to highlight the objects that you're interested in. You could do that one by one, or you could run the auto threshold. And this, I think, is also useful if you're starting out from the beginning, is you can just tell ImageJ, try them all. And so if we take the canonical blobs image that you get in your ImageJ download, you can get the output of all 17 different threshold tools. And you can see for this particular data set, they're all kind of similar. The blobs is a pretty robust image, but you can see that some work better than others. But overall, we're pulling out the blobs, but if we kind of hone in on some of the things, they're not all the same. Okay. So now if we want to compare those threshold models, so we're working with the chloroplast image here, we have our original. And so if we just take that original image and start to run the thresholds, so this is the same concept as before, we can see that thresholding off of the raw, it works, right? We pull out some of those chloroplasts. You can see that the upper left, the Schoenbag, it only pulls out the peaks. It's looking for the greatest difference. Whereas in the bottom right-hand corner, we have the minimum error or percentile, and that gives us a lot more specular noise. We want to try to have a nice, clean thresholded image, and so trying to avoid those two extremes. And so we'll typically do some pre-processing. And so this can be a median filter, which in ImageJ you have the ability to adjust the kernel size for. You could do a Gaussian, and those are typically the two smoothing filters that I'll lean on to do some of my pre-processing to give me a better image. And so this has had a median filter applied to it. And so you can see it looks a little smoother than before. We makes the grana in the chloroplast harder to see. But now when we go through and do our thresholding, it gives us these smoother selected objects to go for. Again, Schoenbag still not the best one for this particular data, but now we look at moments in Atsu, mean, Renyi entropy, intermodes. They're giving us a clear selection or an outline as to where our objects of interest are. Looking at it this way, and from a quantitative method, we can see that there's different amounts of pixels that are selected and processed. And so we see these big changes, like the big change from percent increase on some is really a small amount of the percent of pixels processed. You don't want to over-select or under-select. And I think that that's probably the most important part of when you are doing that thresholding, right? We want to hit that border of where your object is and not pick the background or exclude where any sort of drop-off is. Concept check for thresholding. So your threshold is based on intensity values, right? We're saying anything above this certain amount is an object and anything below is the background. This output then gives us this 8-bit binary image where 0 is black and 255 is white as the only intensity values. different threshold models are going to give you different results. We saw that on the previous slides where we're seeing a little bit more noise. We're seeing some things don't select them all appropriately. It truly depends on the goal of what you're trying to extract from that image. Pre-processing can help clean up your thresholded image to give you a better result. And so that'll give you an enhanced or a smoother binary image. Now, is there some sort of quiz we're doing at this point, Emery? Oh, hey, look, it popped up. Nice. Nice. How do I know when they're done? Do I get a thumbs up or do I keep plowing through? 30 seconds. I think I can tell on my side.
We've heard from about half our participants, so maybe another 10 seconds if that works.
Thank you, Ken. Oh, super. There we go. Okay, so it looks like everybody's in, and yeah, so right, you know, our out bit is going to be that 8-bit binary. That's, I think, the one that tripped us up, but you know, it's out of 255 values, so it makes it 8-bit. Let's just check the chat real quick, and Emery. Great. So now we're going to move forward. So when we think about pre-process, and we're going to get back into this, is there are multiple things that are can contribute to what your background is. And so autofluorescence, crosstalk, bleed through, ambient light. And so those things, you should do your best to decrease during your acquisition, but sometimes they are unavoidable. And so we can do a background subtraction. And so this is going to either apply a single value and subtract the whole space, or we're going to define a rolling ball that's going to move through and subtract where the background is. When you're doing a rolling ball, it's moving across the image, and the radius should be at least as large as the largest object in the image. And they're saying it's also, sorry, the rolling ball in image A is not a true circle. So something to consider when you're selecting your objects or setting your filter. The other things, and this is what I had mentioned before for myself, as far as using the process filters can smooth those objects and to help kind of clean up the noise that you get from your acquisition. Okay. The important thing, and this is true for all of this because we want our acquisition and analysis to be reproducible, is to report as much information as possible. Not to overwhelm, but at least for someone to sit down and go, oh, okay, this was the raw data. This is how they got to these results. So we can see and potentially repeat it ourselves, right? That's the goal. And so samples with heterogeneity in the background and a high dynamic range tend to benefit from rolling ball more than manual subtraction. So this is an image of liver tissue. So we're going to go through and do some background subtraction on this to help kind of extract the information that is there. The important thing is you want to be consistent. So we have our original image on the left. In the middle, there's a manual subtraction. And on the right, there's a rolling ball. And so we can see, depending on how calibrated your monitor is, your original image was a lot more grays. The manual subtraction, your blacks become more black. We're lowering that noise floor to close to 0. And then we have our rolling ball. So now if we go through and apply a thresholding tool to that, we can see in the original, we get that specular noise, great. The original and the manual subtraction yield about the same result. And so that could potentially be over measuring, right? We're selecting maybe too many pixels, a lot more of that fine detail. And the rolling ball is potentially pulling out the peaks of where our objects are. So we're getting slightly, well, getting less objects defined in that threshold. So now we're back to our image. And if we apply a pre-processing filter, and this is somewhat subtle depending on how fast I flip back and forth, raw data and then process. So these have had a pre-processed filter put on them. They've smoothed out. So there's a median that is on there. And now we go through and do our manual subtraction on the rolling ball. We can see that the output threshold image is smoother across the board. And our selected percent pixels between the manual subtraction and the rolling ball, we're again sticking with slightly more pixels than the first one. So it was like 16% and change without the subtraction. And now we're up to 17.5. And it comes down to, when you look at your raw data, are these thresholded areas in the object you care about or not? We want to make sure that we're accurate with that. So on the right here, we can see this table, and it's just showing the difference in the selected pixels between the two. And so filtering and unfiltering between the original doesn't really change a whole lot, right? It's when we start doing this rolling ball subtraction that we see that change, where we're not, especially if you look at the thresholded output, it's smoother. We're not going to get a lot of those selected or specular pixels, which are going to end up, if we go into analyze particles, potentially showing up as measured objects. And so if we can get rid of those ahead of time, it'll make our life downstream a lot easier. Now we need to think about the bit depth of our data when we're doing this threshold. So on the top, we have our original 12-bit image, and it was thresholded with 3 different methodologies: Otsu, mean, and triangle. And so Otsu is the best for a bimodal distribution. It helps pick out those objects where there's a clear dip between them. The mean is taking the mean intensity pixel values of your histogram. And then triangle is good for a unimodal histogram distribution. And so now, if we keep it at 12-bit, 8-bit, these two images, top and bottom, from a 10,000-foot view look about the same. But if we hone in on some of these spots here, on the top, we can see this, at the point of this green triangle, this opening, right? And so now if we did that in 8-bit, we see it's actually closed that little gap. And so if we ran a fill holes command after this, we would then lose that information, right? It would fill in that space, or would over select, depending on what direction we're using our binary here. For this one, we're generating more holes in the 8-bit, and then for the triangle, we're losing pixels to quantify. So being aware that the bit depth change is going to impact what you get to define as your object of interest. Sorry, I have the window popped up here. So you need to compare the bit depth and other pre-processing steps on how it's going to impact your thresholded results. And so sometimes scaling down in bit depth might help it process faster, but the decisions are going to change your results. And so using the mean threshold as the example, we have now, if we go back to our chlorophyll or chloroplast images, and so we have our original here, that 12-bit, and then the convert to 8-bit. We can see along the bottom here, there's a slight change in where the edge of the chloroplast is, from about a handful of pixels. If we go through and do a median, it's similar, right? Some of our external objects get smoothed out a little bit. But now if we do a much larger median filter, and so I applied a median filter of 6 to this, and it really helped blur the edges to make sure, okay, we've pre-processed too far. And so the watershed is able to divide them, but you can see that we're selecting the space that's between those chloroplasts. If we then combine our tools that we've learned, so we do a background subtraction and a median filter, we can now, on the 12-bit, the original top image, you can see that it's, when the watershed is run, select the appropriate amount of chloroplasts and not over divide things or merge things together. And so it's that balance of steps. And so as you go through and generate these various steps in your processing to make sure that it's the best choice for what your data are, right? And we want to do checks throughout as we're going to make sure we're not excluding data, over segmenting, increasing our number of objects, and so on. And so we're at our concept check 2. So thresholding and pre-processing, right? Processing an image before thresholding will change the suggested threshold value with each pixel at threshold. And so this smoothing out will allow the threshold to work better, potentially. And this can also include background subtraction, filtering, changing your image type or bit depth, and other things from those pre-processing menus. When you choose what works best and when you find out what works best for your images, be consistent. You want to apply everything across the board to your controls and the samples of interest to make sure that what you extract is exactly what you're trying to analyze. I think, Emery, that is where I'm handing off to you. Or wait, we're doing a quiz. Need a little countdown slide.
Yeah, it looks like we have about half, so I'll do like 10 more seconds.
All right, last call for the poll.
Perfect.
There you go.
And now we all still see this. Okay, perfect. Thank you everyone for participating in that. So, okay, it's back. So now that we've introduced global intensity-based thresholding and optimizing this outcome with pre-processing, it's important to remember that the ultimate goal is segmentation. And there will be times when intensity thresholding alone will work well, including this chloroplast example that we gave, but then also times where it won't work as well, and we don't have optimal segmentation of our objects of interest. Structures with high dynamic range, so a larger intensity difference between dim positive signal and bright positive signal, as well as maybe smaller or more complex structures, tend to require more than just intensity thresholding in order to segment these objects. And so we just wanted to point out that previous sessions and also a mini workshop, which you can take at ABRF this year, include some trainable segmentation plugins. And the more popular ones in ImageJ are trainable Weka segmentation and LabKit. So both of these will train and retrain based on user input to perform Weka pixel classification. So this is a type of machine learning, and both of these can be applied to 2D and 3D images. A typical workflow is selecting the class features that you want to train on, giving user input for training data, including just little traces of these pixels are foregrounds are part of an object or backgrounds are not part of an object, and then training the classifier. You can reassign classes as needed and retrain as needed iteratively until you reach your optimal result. The result being you want to have a binary image that will well represent your original data. Once you have this, we can talk about binary processing options. So we just talked about pre-processing, thresholding, which is a form of segmentation that's just global intensity based for your images. And then the next would be processing this 8-bit binary image in order to make regions that are better representative of the original. For example, we have these three objects that are touching. And so with just looking at intensity, they're one big object. And as well as this and this over here, we see that we have local regions that are a little bit dimmer and they did not make the threshold that was chosen. And so they are little holes. So through binary processing options found under the process submenu and then binary, you can fill those holes, which was talked about back in November. And then also you can separate objects. So like I said, filling holes, erosion, and dilation are all processes that were covered in a previous session. When we talk about water shedding, we're talking about estimating object edges to approximate where to separate those objects. This can also be accomplished through erosion and dilation, as previously covered. Some other options that are not as common but might be useful include outline, wherein you keep a single pixel wide outline or boundary pixels and remove the inner pixels from these regions. This can also be accomplished with image math through erosion and dilation. And an example output of that is shown here. We have the outlines on the left and then putting it on the regions on the right. Another option would be skeletonize, which removes the outer pixels of an object and keeps a single pixel wide inner line for each object. So this works through kind of mass erosion, and then you eventually come to these single lines. So over here, we see that even though this is one object, due to the shape, it kind of makes a little bifurcated line over here. This is actually a really bad example of when to use skeletonize. The skeletonize process is most beneficial for linear structures. So in a different example, this is a Golgi image for the Golgi apparatus, lovely linear structures. After some pre-processing and making a binary through intensity-based thresholding, we have this, it looks kind of funky. And so through the skeletonized process, we can return to a nice approximation of the linear nature of the Golgi. So we have another concept check, and this time I'm actually going to pause and let you answer the single question first, because we didn't really go through a lot. And Erica, I don't know if you have, there it is, perfect. Thank you, Erica. Beautiful. I'm going to end it soon, but the keyword here is not an example. So filtering is not an example of binary processing. Oh, I can share results from here too. Nice. Okay. So the reason we would do binary processing is, again, because after we do the thresholding, now we have regions, but we want to make sure that they best represent the original image. Common options include filling holes, erosion, dilation, and water shedding. And all these and more can be found under the process submenu. So now that we've talked about how to obtain these regions, how can we convert it into a region that we can use for measurement down the line? So for this, we're going to start talking about analyzing particles through the Analyze submenu. Under Analyze submenu, you can find Analyze particles, and mainly we want to use this to add regions based on the binary image to the ROI or region of interest manager. This will then make it easier to use those regions on any image that's related to the regions that you made in order to do measurements. The Analyze Particles menu also offers different criteria to include or exclude certain regions that you got out of the binary. So let's say that you have something that well represents your original image, but again, we're doing a global intensity threshold. So maybe it's picking up some things that you don't really want included. You can include exclusion criteria. So this is what the Analyze Particles menu looks like. And so you can exclude things based on size. 0 means that anything, it'll include anything like as small as possible. Up to infinity means that there's no maximum size. And so, for example, if you want to exclude very small objects, you would add a minimum size exclusion. And then if you want to exclude larger objects, you would add a cap saying nothing larger than this. You'll notice that it's in microns squared. A lot of the fluorescent bioimages that we work with have something on the scale of maybe microns. And so that's why it says that. If you want to work in pixel land, you can check off the pixel units box. And then from there, the size will instead be in pixels and not microns. Another criteria that you can include or exclude objects based on is circularity. So that's just a measure of how circular something is. 0 means it's not a circle, and 1 means that it's a perfect circle, matching in both directions. And so, for example, let's say for these chloroplasts or like DNA or something, if you're looking for like a nucleus, if you're looking for something that's more circular, and you also have some bright areas that are really not circular, you would increase the minimum circularity here. The Show drop-down menu offers region display options as either overlays on your binary image or it generates an additional image. So for example, the overlay and overlay masks options will result in your binary image having either an outline on your regions or a colored overlay on the whole object respectively. And so this is an example of what that looks like here. So the outline here is in a yellow-orange color, and then the overlay mask will give you a different color for each region. Your outlines, bare outlines, and ellipses options will generate additional images, and they all yield dark outlines on a light background. The outlines will include the numerical labels, bare outlines will not, and ellipses will stretch the regions to fit an elliptical shape, and so that's what this looks like. So again, outlines will give you the numerical labels or the counts here. Bare outlines won't. And then finally, the masks and the count masks. So these also yield additional images. The masks one will have a dark foreground and light background, whereas count masks will yield a linear relationship between the numerical count or label and then the intensity output. And so that's what that looks like. And so for count masks, what you might need to do is adjust brightness and contrast to make things more easily visible. So our darkest region over here, very hard to see, was labeled as number 1. The brightest area was labeled as number 9. So that's where this linear relationship comes from. Down to the lower part of the Analyze Particles menu, when you display results, it'll display your results table filled with measurements that you have selected from Analyze and Set Measurements. Sometimes you won't want to display this. If you want to take the regions from here that Analyze Particle selects and then use it to get additional measurements like intensity-based ones with your original image, because the size and shape will be the same. So if you leave it unchecked, you could just apply it to an image afterwards and it'll be okay. If you have clear results checked, it'll clear previous results from your results table. This is useful if you've been doing a lot of measurements and you don't want to append it to hundreds of lines already. And also if you don't use the display labels feature, display labels is something that will help you see what measurements are going to what image, what region, etc. If you have summarize selected, you can get a results table of a summary of all the measurements that you've done. It's just giving you averages of everything and counts and things like that. When you have add to manager selected, which we would want you to do, it would add all the regions that meet the Analyze Particles criteria to the ROI or region of interest manager that you can then use to apply to other channels, images, etc. When you have exclude on edges selected, objects that are touching image edges in X and Y will be excluded from measurements. A lot of people like this because if you try to include those objects, they're incomplete objects, and so a lot of your measurements will be incomplete. If you, for whatever reason, have justification to include them, then deselect this checkbox. Include holes and composite is where it might get a little tricky for you. When you include holes in your binary image, the ones that are not filled. So if you didn't go to process binary fill holes, it will include those areas in that region for size measurements. When it's unchecked, the ROI is not including that hole for the measurement, but you won't see a trace around the hole because that would make it a composite, which I'll get to in a bit. The overlay checkbox will give you the overlay outline similar to the show overlay. Composite ROI, this is what I was just mentioning. It will result in excluding the holes as long as include holes is not selected, but it will also give you an outline around the holes. It's a composite because there's two different things in one area. So for example, I didn't watershed this. And so if I click include holes and analyze particles, this entire island of our different objects will include the holes in our area measurement, and that yields about 195 microns squared. If, again, I take the same image, but I have include holes deselected, just like how it is in this image, it won't include these holes of the what it's considering background in the binary image in the area measurement. And so we get about 192.7 microns squared. When I fill the holes, that results in the same area as me saying include holes, which is good. That's showing you that it's doing its job, even though it's not selecting it. If you do not want to include the holes, so I have include holes deselected, and I did not fill the holes before, but I checked off composite, it will still exclude the holes, but give you that composite selection, which is the additional outline of the holes. So that's include holes and composite. So now that we've brought us through most of the pipeline, let's talk about moving from analyzed particles, doing the exclusion criteria to make all those regions of interest and bringing it into the ROI manager. So the ROI manager can be accessed separately. If you go to the Analyze submenu, then Tools and ROI Manager. If you also manually make a trace and use the T key, it'll pop up as well. And it's automatically opening when you're done with Analyze Particles, as long as it's selected and you click OK. So once the ROI Manager is up, you'll see a list of regions over here on the left-hand side. There's none there now. If you are manually drawing regions with an ImageJ tool, you can click this Add button or use the T key to add your drawn region to this list. If you select a region from a list, like let's say you want to remove it, you can select it and click this Delete button, and it won't be measured, and it will also be excluded from everything else. It just no longer exists. Whenever you select a region from this list, it will be highlighted in blue, like a dark blue. And you can also select singular regions to measure individually one at a time. You can also select multiple ones or just deselect, and if nothing's selected, it will measure all of them. Note that whenever you're doing measurements, it's being performed with these regions on the image that you have currently selected in ImageJ itself. ImageJ is selection based. So if you last had clicked on or did something with the binary image, all of your measurements will be done on that binary image. And so again, like if you're looking for intensity values, it'll all say 255 because that's all that we have, because it's an 8-bit binary and not like a 1-bit, so 0 or 1. And so to do measurements on something else, you would select another image or channel and then click the measure button, and it'll do those measurements on whatever you previously selected or most recently selected. You can also display the region overlays and their numerical labels in the currently selected image again. And then from here, you can also flatten those in order to make a separate image that's just an RGB copy, but you can have the ROIs and labels displayed as annotations in the image. So that's kind of what it looks like after we had gone through analyze particles, after we did binary processing and did analyze particles. We decided to include this just to show you the outline. And from there, you can click on the original image, click show all and labels so it shows up, and then click the measure button to get all the same size and shape measurements, but also include intensity measurements. We talked a lot about getting measurements. We don't have time to get through all the measurements that are options in ImageJ, but you can see them all under the Analyze submenu again and Set Measurements. Here, what we had popped up at the very beginning of the talk included area, the mean intensity value or gray value, the shape descriptors, which are aspect ratio and circularity, and then ferrets diameter will take the widest points in your object and give you that length. And so again, those were these values. They're fun to look at. So now we've been talking a lot about looking at regions and doing all this processing and analysis with 2D single channel images. Realistically, you're going to have more dimensionality to your images. And so this is a quick example of comparing the intensity of two different channels within the same region. We would use one channel to make a mask for the binary image in order to get the regions so that you would obtain the same size and shape measurements, but then specifically compare intensity of the two different channels in the raw image. So this is another plant example, and we have two different populations of chlorophyll. So we'll use those two, the magenta and the green, to look at. And because we can see that the magenta is more dominant, we're going to use that to create regions of interest to add to the ROI manager and compare it with the less dominant green signal here. These regions are then applied to both channels separately, the green and the magenta, and then after applying it to each, we click the measure button in the ROI manager in order to get these measurements. From here, you can either measure one channel than the other to have it append to the same results table and then just sort it out in Excel or whatever you want later. Alternatively, you can get measurements from one channel, save that, then get measurements from another channel and save that separately as well. It's definitely up to you. What you can also do just for simplicity is have the channels merged and show the region overlays on the merged image so you can see where we're looking at. So you can see where there's definitely areas where there is very little green signal, maybe some more green signal. And then you can bring it into a greater context of your sample overall. So you can see that where there's this chlorophyll, we're not seeing a lot of this lignin, this cell wall type thing. From here, we kind of chose this area seemed to have a little more green signal than this area, and we can verify it quantitatively by looking at the average intensity measurements in the green and magenta channels. And we can even see that in this region, if we kind of normalize a little bit to the magenta, the green intensity is about 54% of the total or the average total magenta intensity, whereas the green intensity in this area of the sample is only about 32.5%. What you can also do is apply ROIs to different channels over time. So now we're adding in the time dimension. So in this comparison, we're looking at the change in intensity of a photoconverting dye. Thank you, AQLM. So instead of measuring mean intensity value in a large area, so making the square or rectangle and measuring the intensity within the square or rectangle over time, that's less precise, and it would include more of the backgrounds, which will sway your results. We can have ImageJ automatically threshold one channel at each time point to generate ROIs. So here, the dominant channel is green. I would use the green channel to make ROIs and compare the intensity at each time point of green and magenta, and then we can make a graph out of it. So for example, towards the beginning of this time lapse, towards when photo conversion starts, and then towards the end of the time lapse, we're getting these larger regions, and we can compare the intensity values between the two channels for all the time points, not just these three. And so we would get something that looks like this. The mean intensity value of green decreases, the mean intensity value of magenta increases, and we see it starts to spike. And because the intensity values are disparate between these two, we can normalize the starting intensity for each channel individually and see that overall, we do see when photo conversion starts, we see this larger spike in the magenta signal towards the end. almost at the end, so we have one more concept check. And then I did not master this, but I think, Erica, you were really good at popping up the little poll question. Let's see if I can find. While that's happening. So why are we using analyzed particles? Even after binary image processing, we might need to use other criteria in order to exclude or include regions to measure. Excluding objects on image edges, X, Y, and also Z for Z-stacks is common, as these would be incomplete measurements. There are some examples where you can include them though, and as long as you can justify it and you remain consistent, that's key. So I hope that throughout this and all the other ABCD sessions, you've noticed that consistency is key. Size and circularity criteria can be used to exclude certain regions, and that's also accomplished in analyzed particles. And through this, you can also add regions to the ROI manager, which allows you to measure the same regions in other images and channels as well. So, oh, here. Okay, I'll pause a little bit and have people choose. Awesome. So how we obtain regions from binary images is using those analyzed particles. Perfect. And so now what I also want to talk about is some other options. So for example, if you want to look at 3D thresholds, there is the 3D objects counter in ImageJ under the Analyze submenu, and it will create a threshold mask of an image to be used. You can, in the 3D OC options, redirect that binary to an image selected out in ImageJ, and that will make the measurements that you want. If you have none selected, it will perform all the measurements on that binary image, so you can't rely on any intensity measurements. And it might take some time depending on your file size and the features. It's important to note that this only works on 8 and 16-bit images. Another option would be 3D Sweep, which is a plugin, and it will be available in the plugin submenu after you download it through Manage Update Sites when updating ImageJ. The benefits of 3D Suite are there's a little more binary control and more options for selection and processing before you go to measuring. A lot of the measurements are similar with some additional options in 3D Suite, for example, areas of the image or separating measurement types. But some considerations are it is more involved, so it's more of a learning curve. And though there are several options, a lot of processes and analyses can be much slower depending on your file size and your bit depth. So even regular intensity thresholding, as we mentioned before, if you do have 16-bit images, you will want to use the 16-bit histogram, but it just takes longer to include all of those bins in the intensity threshold, which is why ImageJ defaults to the 8-bit. As a little recap, we just covered some basic global intensity thresholding with ImageJ, and you can accomplish all processing your original raw data, the intensity thresholding, and other segmentation, binary processing, and applying ROIs for measurements all in ImageJ. ImageJ's intensity-based thresholding results in an 8-bit binarized image for 0 or 255 and not 0 or 1. I think that a lot of the LabKit application will give you a 1-bit or 0 or 1. And that's just because downstream processes and analysis with ImageJ typically look for an 8-bit image, and that's the only reason that ImageJ does this. The models used for intensity measurements will determine whether or not an object, whether or not a pixel is part of an object or not. And thresholding is just another segmentation option that can be used for consistency in measurements and your data sets. So with that, are there any questions? And also please remember that ABRF 2026 is happening in March, and we have the mini workshop will go more in depth with automate more like machine learning and automated segmentation options. Let's see if there's questions. Okay, so one question is it better to use the same threshold on a set of images, or can auto thresholds be used for each image? What I know I would recommend and what we had talked about is using auto threshold at first to see automatically how the different options process your sample. All of them are just using different math in order to figure out, okay, like this is one thing versus another. So like Otsu is a very popular one, and it's just looking at maximizing variance between the two different classes, like object or not an object, and then also minimizing variance within each category. And so it's really just deciding which one will be the best in general for your data set. So trying to use the same model for your data set is recommended generally. It also makes things easier if you do go to more, I guess, like batch processing or larger processing if you want to include this in like an image day macro or something. If there are no other questions, I stopped sharing. And we are going to be sharing these slides and also the images that we use. And I compiled some of the papers that have been published about these thresholding models. So be on the lookout for that. Awesome. If that's all, thank you everyone for joining.